Today, we are diving into one of the most elegant and profound concepts in all of physics. For decades, this was a massive puzzle for physicists. It was a real headache. They knew that some particles, like the W and Z bosons that carry the weak force, had a lot of mass. But then you have the photon, the particle of light, which has absolutely no mass at all. Why? The Standard Model, our best rule book for the subatomic world, just couldn't seem to explain it without breaking its own rules. And then the answer turned out to be hiding right here, inside this one single beautiful expression. It might not look like much, but I promise you it holds the entire secret to how fundamental particles get their mass. So let's unpack this thing piece by piece and see how it works. Okay, to really get what this equation is telling us, we first need to meet the two main characters in our story. We're talking about a scalar field and a gauge field. They are the fundamental players in this whole cosmic drama. So first up, we have the scalar field, which we write down with the Greek letter phi. The easiest way to think about a field is just something that has a value everywhere in space, kind of like the temperature in a room. Well, the scalar field is like that. It's this fundamental energy field that fills the entire universe. You can think of it as a kind of cosmic molasses. It doesn't point in any direction, it just is. It has a value at every single point. And if that scalar field is our background stage, then our second character, the gauge field, A mu, well, that's the messenger. This is the field whose ripples, whose excitations, are the force-carrying particles themselves. We're talking about things like the photon for light, and you guessed it, the W and Z bosons for the weak force. Right, so these two fields don't just exist separately. No way. They talk to each other, they influence each other. And the rulebook for that interaction is one of the coolest ideas in physics, and it's all wrapped up in a concept called the covariant derivative. And here it is. This is that covariant derivative. This is the D from our mystery equation. Now, don't worry about all the symbols right now. Just think of it as a set of instructions. It's the mathematical recipe that tells our scalar field how to behave when it's moving through a gauge field, like the one for the weak force. So let's just quickly walk through how this rule works. The first bit, that delta mu, that just tells you how the scalar field would change all on its own, just moving from one spot to the next. But then, the second part, the part with the A mu, that adds in the influence of the force. And when you put them together in this very specific way, it makes sure the laws of physics look the same no matter how you measure them. It's a deep principle that physicists call gauge symmetry, and it's absolutely crucial. Now, this is where the story takes a really cool turn. We usually think of a vacuum as just empty space, right? The lowest possible energy you can have. But it turns out, in our universe, the vacuum is not truly empty. And the reason for that is a phenomenon with a great name, spontaneous symmetry breaking. I love this analogy. Imagine balancing a pencil perfectly on its tip, okay? The laws of gravity are totally symmetrical all around it. But is that stable? Heck no. To get to its lowest energy state, the pencil has to fall over. It picks a random direction, and in doing so, it breaks that perfect symmetry. Our scalar field, which we now know as the Higgs field, it does the exact same thing. Its potential energy is shaped like a Mexican hat. The lowest energy point isn't right at the center, where the field value would be 0. Nope, the field rolls down into the circular brim of the hat. And what does that mean? It means it has a constant, non-zero value everywhere, even in a total vacuum. We call this its vacuum expectation value, or V for short. So here's the million-dollar question. What happens to our original equation when the Higgs field isn't 0, but is settled down into this constant vacuum value V? This is the key. This is what unlocks the entire mechanism. So let's go back to that original term. We're back where we started. Remember, this whole expression represents the energy of motion, the kinetic energy of the Higgs field as it interacts with the universe around it. So now let's look at this interaction in the vacuum, in that lowest energy state. In this state, the Higgs field, phi, isn't flying all over the place. It's settled down to its constant value, V. So all we have to do is replace phi with V in our equation. And the next step, this is the beautiful part. That first term, delta mu V, is asking a simple question. How does the constant V change from one place to another? Well, a constant, by definition, doesn't change, so its rate of change is 0. That whole first part just disappears. It goes away. So when the dust settles, all we're left with is the second part of the expression, squared. And when you work that out, something incredible, something that was hidden there all along, just pops out. You get this new term, E squared times V squared times the gauge field A mu interacting with itself. Now, to a particle physicist, seeing a term that looks like this is a huge deal. Why? Because in the language of quantum field theory, any term in your equation that looks like a number multiplied by a field squared, that is a mass term. That's literally the definition of mass in this framework. It's what gives a particle inertia. You can just line them up side by side. The term that popped out of our equation has the exact same form as a generic mass term. And just by comparing them, we can literally read off the mass of the gauge particle. It's the coupling strength E times that vacuum value V. It's not magic. It's just the consequence of a force-carrying particle trying to move through that cosmic molasses of the Higgs field. So you might be wondering, wait, what happened to that symmetry we broke? Doesn't that usually create a new massless particle? And you'd be right. But in this special case, that would-be massless particle gets eaten. The gauge boson absorbs it, and in the process, it becomes massive. It gains a whole new property that it didn't have before. And this incredible idea was first worked out way back in 1964. But it took almost 50 years of searching, building bigger and bigger machines, culminating in the monumental experiments at the Large Hadron Collider to finally find the particle of this field, the Higgs boson, and prove that this is really how nature works. So from one tiny term in one equation, we get the origin of mass, completing the standard model of particle physics as we know it. It's just an amazing testament to the power of symmetry. And it really makes you wonder, what other incredible secrets about our universe are hiding in plain sight, just waiting for us inside the language of mathematics?